Saxon Advanced Mathematics, lesson 109. Oh my gosh, students, should be a fairly quick little lesson. We're combining some older ideas and putting them together in a new way. So we want to talk about rational numbers. You remember, I'm sure you do, that rational numbers are all the numbers that can be expressed as a fraction. Okay, if you can write it as a fraction, then it's a rational number. And despite what might seem like the intuitive call, if we have infinite repeating decimals, right? So any number that goes on infinitely but has repeating decimals, they are rational numbers. That seems weird to think of because if the decimals go on forever, how can they be rational? But if we can find a little trick that allows us to express them as a fraction, then we're good to go. We found such a trick back in the waning days of Algebra 2. I won't go into details about it, but we did do a fun little lesson that showed us a way to express those infinite repeating decimals and prove that they're rational. Remember, I recommended that you bring it out at parties. You know, if things get kind of slow, you can show everybody how to express infinite repeating decimals as rational numbers. I'm sure you've used it. There's no question in my mind because how fun is that? But today we're going to learn another way to do it. And we're going to use that lesson that we did, not last time. Last time was matrices, but the one before that, I'm looking to see what number it was. 107, Convergent Geometric Series. We learned that if the R value, the absolute value of the R value is less than 0, we have something called a convergent series. Remember, it's a series because we're adding together all the little pieces. And you can use a stripped down version of the formula. And you just take the original amount and put it over 1 minus R. That allows you to calculate the total of a convergent series where the absolute value of the ratio is less than 0. This keeps getting smaller and smaller and smaller and smaller and smaller. And eventually it gets so tiny that it becomes nothing, and we can basically whack it out of our equation and use something simpler. So let's use this. I think I've told you enough to be dangerous. Yes. Okay, so let's dive in. There are only 2 examples in this one. Okay, use an infinite geometric series as an aid in writing 0.0023 and just the 3 repeats as a common fraction. Okay, so what we want to do is we want to draw a diagram of this number as best we can. That always helps us break it down. So the first thing that occurs to me is to write this as I'll put a 0 in front just for fun, 0, 0, 2, 3, and then the 2 3's repeat, right? So I'm gonna write a few of those repeated, and I'm gonna put spaces in between them just to help me see that's where the repeats are. Now, it occurs to me, I can write this as a series because this is the original amount, right? So this is my A1. And then I'm going to add to that this second set of 2 3's, but instead of it just being 2 decimal places hanging out in space, I'm going to create a whole number that it represents. And then this, 2 more zeros. Here's our next 2 3. I know it's weird spacing, but I was trying to make that come down to show you how these correspond. And then this fourth set, 0, 0, 0, 0, 0, 0, 0, 2, 3. It's like a geometric series, isn't it? We're adding a number and we're multiplying each time. Let's see, what are we multiplying by? Let's see, this one we could write as 23 times 10 to the what? Minus 1, 2, 3, 4. Now that's not proper scientific notation because my decimal could be there, but this makes more sense for what we're trying to see here. Now, when I go to the next level, it's 23 times 10 to the minus 4th, my original number, and then I've moved the decimal place. I've put 2 more zeros in here, so that's the same as multiplying that times 10 to the minus 2, isn't it? See what's happening? We're rethinking this repeating decimal as a convergent geometric sequence. My common ratio, which I've developed right here, is less than 1, right? We'll look at it in just a minute, but I know that 10 to the minus 2 is a number less than 1. Let's just look at this one. This would be our original number, 23 times 10 to the minus 4, times 10 to the minus 2, right? So there's 1, 2, 3, 4. There's my original number. Did I put the right number of zeros in? Let me check. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2. No, I need one more zero here. There should be 6 zeros because here are the 4 I had last time, and I added 2 more to bump that 23, 2 more decimal places down. So this is times 10 to the minus 2 again. And I could write it for this one. Let's see if I have the right number. I don't. I'm missing a 0 here as well. There should be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So there, now I fixed it. So what we find is that our A1 value equals 23 times 10 to the minus 4. And our common ratio equals 10 to the minus 2, which is also equal to 10 with 2 decimal jumps back, right? So that would be right? Because if we move this 2 jumps, then we get our 1 back, okay? So 10 to the minus 2 equals 0.01. These values came from this way of understanding our number. We're going to do this again so you'll get another chance to understand. I know this is a little trippy, but see how we're just making this pattern? Now we can take these numbers, put it into this formula. Oh, and P.S., we did verify that our common ratio is less than the absolute value of 1, so we're good with that. So I'm going to recopy my formula to the back of the page. The total of the geometric series is the original amount over 1 minus r. Our original amount is 23 times 10 to the minus 4, and our common ratio is, I'm going to write it as 0.01 here because I want to subtract it. It was also equal to 10 to the minus 2 because we kept jumping back 2 more decimal places each time. Now, I just want to point out to you, how many decimal places repeated in our number? 2. Our common ratio was 10 to the minus 2. Keep that in mind. We're going to use that next time as well. Okay, so now we're ready to plug in. So the total of all of these things added together is 23 times 10 to the minus 4 over 1 minus 0.01. All right, I'm just plugging this in. This looks a little scary, but it's okay. I definitely want to use this form because I have to subtract that from 1, and I don't want to subtract, I don't want 1 minus 10 to the minus 2. No, that does not look good to me. So I chose to use the decimal version of it. That gives us 23 times 10 to the minus 4 over 0.99. Okay, again, this is an ugly mess, but it's okay. We'll figure it out. We're almost there. The last thing we want to do is we want to get rid of this. 10 to the minus 4. So what we're going to do is multiply. I don't know that we've ever really done this before. We're going to use the product rule to solve this. If we take the minus 4 and then we multiply it by 10 to the 4th, the product rule tells us we add those, we'll get 10 to the 0, and the 10 will completely drop out of the calculation. So this goes to 10 to the 0 power, which is equal to 1. It goes away. Our new denominator is 23. And our denominator, 1, 2, 3, 4, we'll fill in a couple zeros. Our denominator is 9,900. Whoa, that's pretty cool, right? And you'll remember, if you remember that lesson from Algebra 2, we always came up with fractions like this. Our denominators had lots of 9s in them, and they were super weird, quirky fractions. But hey, that's a fraction, so that proves that this number, which was where we started, is indeed a rational number, okay? Remember that we wrote this using a power of 10, and then the common ratio was a power of 10, and the negative exponent on that just happened to be equal to the number of repeating digits. Okay, let's do another one and see what the pattern is for this one. 109.2. Use an infinite geometric series as an aid in showing that 5.013 and all of that is a rational number by writing it as a common fraction. Okay, so spoilers, just take note of the fact that this number has 3 repeating decimals. It's also got a 5, which is going to confuse things a little, but not a lot. Don't worry about that. So we know that this number is 5.013, 013, 013, and so on. Let's break it down like we did last time by writing it times powers of 10. The original number is 5 plus 0.013. And then we're going to add 0.000013. So we add those zeros in order to make the pattern repeat the right way. 0.0000013. So now we have 2 sets of 3. All right. So let's write this as we want to keep the 5 separate. He's not really part of this repeating pattern, so we can't ignore him, but we don't want to write this as the number 5.013 because the pattern is just based on multiplying this part of it. This is 5 plus 0.013 times 10 to the minus 3, right? Because we have this, there's the 013, but then we're multiplying it by 3 more decimals to the negative, right? So there's that. This will become 5 plus 0.013 times 10 to the minus 6. I put little squiggles under my zeros so you could see the groupings better. I should have done that last time. There's the original 2, then there's 4, and here's 6, and here's 8. It helps if you can see those extra sets of zeros coming on. So what we can see is that the 5 is going to sit by itself. We're going to add that into the back of the answer. But our sequence is based on an A1 value of 0.013 and a common ratio of 10 to the minus 3. Just like I pointed out, the negative exponent on the power of 10 for these problems is always equal to the number of digits that repeat. okay? I don't know how to write that in words without writing a Wikipedia entry. Well, some of those are short though, so never mind. I don't want to write a big long book. I want you to just see the pattern. 3 repeating decimals is what triggers that number. Notice it's always a minus because our pattern is getting smaller and smaller and smaller, but that's always the way it will work. Okay, so now let's make this pretty fraction. 0.013 over 1 minus, okay, we want to write this as a decimal number because I don't want to subtract 10 to the minus 3 from that. So this would be 0.001. Okay, 10 to the minus 3, so we move the decimal place 1, 2, 3 times. That's not right. 10 to the minus 3 10 to the minus 1 equals 0.1. 10 to the minus 2 equals 0.01. 10 to the minus 3 equals 0.001. There we go. That feels better. So we want to subtract 0.001 because that's the value of our R, right? Remember the formula is okay, so this is the formula we used. We plugged in our values. We rewrote R from being an exponent to a decimal number. Here I thought it through because my brain was kind of going sideways. But there I proved to myself this is the right number to go here. So now S equals 0.013 over 0.999. We're going to multiply this top and bottom by 10 to the 3rd power because we want to wipe out those decimals. S equals 13 over 999. Okay, we're almost done. We just have to factor this 5 into the business. So we know that S equals 13 over 999, and we have to add 5 to that. There's 2 ways you could write that. You could take the coward's way out and write it as 5 times 13 over 999. I don't want to do that. You know how I feel about mixed numbers, right? So what we want to do is we want to multiply 999 times 5. 45 plus 4 is 9. 45 plus 4 is 9. Okay, so this would be bottom times the big, and then we have to add the 13 to it. Right? In order to turn this into a improper fraction, you multiply the bottom times the big and add the top. So my final number is 5,008 over 999. That is a crazy number, but it is a rational number. Okay, and then the last thing John points out, I just want to go back to it one more time, is that when we're doing these repeating decimal problems, R will always be equal to a negative power of 10, and that power, the number that you put up here, is equal to the number of repeating decimals. Helpful hint for your homework to save you a little bit of time. Okay, that's the end of lesson 109. Thank you. I hope it made sense. Goodbye.